Alright, continuing on with our titration problems, this is going to be a weak acid and strong base equilibria, and these problems are broken down into several steps. We're going to kind of use this to help you figure out. This essentially is you have a buffer initially, and then once you reach the equivalence point, then you kind of use up the buffer and all will be as originally was. You have to do both stoichiometry, so the little BCA charts are helpful for this, as well as equilibria to consider at various different positions. So before the equivalence point, which would be represented by any of this position along the graph down here, notice this time it's not completely straight. Okay, it's not a straight line. It goes up a little bit and then it kind of levels off and then it shoots up. Before the equivalence point, this is behaving like a buffer. So part of your solution is going to be converted by the strong base in this case into the conjugate acid, and then you'll have one of those problems where you have a little bit of acid and a little bit of its conjugate, which is where you get the buffer. A couple of important points. At halfway to the equivalence point, we've done this a couple of times. It becomes really important to know where the equivalence point is and then halfway to the equivalence point, because that spot can save you a lot of work. If you recognize that it's halfway to the equivalence point, you can see that pH will equal pKa. At the equivalence point, in this particular case, you're making a basic salt, so your pH is going to be greater than 7 because of hydrolysis. So you'll see that all of the acid has been converted by the strong base, but then you'll have that hydrolysis, something plus water, A minus plus water makes equilibrium HA plus OH minus. Okay, so you have to work out with that again. And then finally, after the equivalence point, you will have used up all of the acid, and you'll have excess hydroxide. That one you can get the excess hydroxide concentration, get POH, and then just go straight into pH. So there's a lot of different things that you have to consider in these type of problems. So here we go for exercise number 2. What is the pH at each of the following points in the titration of 25 milliliters of 0.1 molar acetic acid? So that's a weak acid with 0.1 molar NaOH. Again, the first thing that I want to do here is I want to know where the equivalence point is and where half of the equivalence point is. Because in this case, I've got a weak acid and a strong base, I know I'm going to have buffering going on here. So I have my equation, plus OH minus yields H2O and my acetate ion. If I'm starting off with 25 mils of 0.1 molar, so I have 0.025 liters times 0.1 moles per liter of acetic acid. I'm just going to use HA because it's shorter and I don't have a lot of space. And then I know that 1 mole of the acid will react with 1 mole of the hydroxide, which is also 0.1 molar. Okay, so then I can go through here, and when I do all this calculation, I see that my equivalence point is going to be at 25 milliliters of NaOH, which means that halfway to my equivalence point is going to be at 12.5 milliliters of NaOH. So these are good bits of information just to have before you even start. Alright, so let's look at the problem. Before the addition of NaOH, so at this point I have acetic acid, which is weak, so it's going to make a nice little equilibria system. Alright, so I have 0.1 molar, 0 and 0. This is basically a rice problem. The Ka for this, if you haven't remembered it, you can look it up. 1.8 times 10 to the negative 5 equals x squared over 0.1 minus x. Go ahead and cancel out that value. So when I multiply those, 1.8 times 10 to the negative 5 times 0.1, and then take the square root, I get that x, which is the hydrogen concentration, is 1.34 times 10 to the negative 3. And then from that, I can get the pH. Negative log of that is 2.87. Guessing y'all are going to need more paper. Sorry. Okay, so the first part, weak acid equilibria. There's no NaOH in there at all yet, so just a weak acid equilibria. All right, for part B, we have 2 steps here because now we do have some of our base. We're going to need a BCA chart. The acetic acid reacts with the hydroxide to make water and the acetate ion. Again, these need to be in moles. So we've got 0.025 liters times 0.1 molar. And this time we got 10 milliliters of the base. So 0.01 liters times 0.1 molar, which gives me moles of 0.0025 and 0.001. And then we didn't have any of this to begin with. Although we don't care about water, so. Alrighty. So now we have a strong base that's going to force the forward reaction. 0.001 minus 0.001 plus 0.001. So that's going to leave me with 0.0015. Nothing here. 0.001 here. Again, these are moles. So I need to divide by the volume. Total. Total volume was 25 from the acetic acid, plus now 10 from the base. So divided by 0.035 liters. So calculate that, and this gives me 0.04286 molar for the acetic acid. And for the acetate ion, 0.02857 molar. At this point, I can either use the Henderson-Hasselbalch equation, or I can use Rice to help me figure out what's the most appropriate change here, because now we have a new equilibria forming. I'm going to go ahead and use the Henderson-Hasselbalch. So again, pH equals pKa plus log of A minus over HA. So that gives me pH equals pKa is 4.74 for acetic acid. That was negative log of 1.8 times 10 to the negative 5th. That's how I got that. Plus the log of, here's the acetate ion, 0.02857 over 0.04286. So I can do the calculation there. And when I add those, I get pH is equal to 4.563. Sorry, 4.564, since I've got 3 significant figures in my concentrations. So there's my pH value here. Okay. All right, part C is either real easy or real hard. For part C, you can either do exactly what we did for part B, set up the BCA chart, subtract based on the limiting reactant, which will still be your sodium hydroxide, divide by the volume to get the concentration, and then either use Henderson-Hasselbalch or Rice to figure out the new pH. The other thing that you can do is you can go, oh, I'm at halfway to the equivalence point. Therefore, acid concentration equals conjugate base concentration. Therefore, if I use the Henderson-Hasselbalch equation, that basically gives me the log of 1, which is 0. And so pH equals pKa, which is 4.74 for acetic acid. Again, to get that pKa, that was negative log of 1.8 times 10 to the negative 5 from acetic acid's Ka value. All right, at the equivalence point, now here's something that, may just blow your mind completely. Okay, the first thing is we know that we have a complete reaction. We have the acetate ion, or acetic acid, excuse me, is completely reacting with the hydroxide to make water. And now I can say the acetate ion. It's still a before, change, and after. Before, we had 25 milliliters of 0.1 molar, so that was 0.0025 moles. At the equivalence point, we figured out up here that we needed 25 milliliters. Sorry, it's way up here. The equivalence point is at 25 milliliters. So the same general calculation, 25 mils times 0.1 molar is 0.0025 moles here. Water's not going to change, and no acetate. In this case, you don't have a limiting reactant because they are both going to be perfectly used up. So that means that your after is nothing for the acetic acid and the hydroxide, and it is exactly 0.0025 moles for the acetate ion. And again, we need to divide by the volume. Total. 25 plus 25 gives me 50 milliliters, so 0.05 liters, which gives me a new concentration of 0.05 molar. Now here's the part that's a little different than we had previously done. Before, we had a weak acid equilibria where we had to use the Henderson-Hasselbalch or Rice to figure it out in parts B and C. Here, we only have acetate ion left, but we know that that acetate ion will go through hydrolysis. And again, I'm just going to write HA because I'm out of space. Give me some hydroxide there. So I have from here, I plug in and I get 0.05 molar acetate. Don't care about water, nothing here. So minus X, and plus X. So if this guy had a chance to sit for a couple of minutes, it would return to an equilibrium system, which is why for the weak acid strong base or the strong acid strong base, strong acid weak base combinations, you end up with things that aren't exactly neutral or exactly 7. So now we have to find the Kb. So remember, to get the Kb, you do Kw over Ka. So that would be 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And you get 5.556 times 10 to the negative 10. That's your Kb, equals x squared over 0.05 minus x. Cross that off. I'm going to assume my 5% rule works to begin with. I haven't been showing them because we don't really have enough space, but you should be doing them. So X, which is the hydroxide concentration, is 5.270 times 10 to the negative 6. Then I can get my POH, it's 5.278. And then my pH is 14 minus 8.722. Okay, so again, for this one, BCA chart to prove how much was changed into the acetate ion, or just calculate it using stoichiometry. Then hydrolysis of the anion with water to make the acid and the hydroxide, and then use rice using the Kb instead of the Ka to get the pH. The final thing is, after the addition of 26 milliliters of 0.1 molar NaOH, now we have exceeded the equivalence point. So at that point we're going to have more base significantly, essentially strong base. You can either do the BCA chart, or you can kind of think through this logically. If you think through this logically, we used 25 milliliters of NaOH to neutralize the acid solution. Therefore, we have 1 milliliter of NaOH sort of left over, since it's a strong base. That essentially means we have what would that be, 0.01 liters of 0.1 molar NaOH then we need the new concentration. So 0.01 liters times 0.1 molar would be 1 times 10 to the minus 4 moles out of a total volume now of 51 milliliters, 25 plus 26, so 0.051 liters. Gives me a new hydroxide concentration of 0.00196, and then I can get pH again. So POH equals 2.707, no, 2.708, and 14 minus that is 11.292. Sorry, this is so messy. Maybe I'll try again someday. Good luck! Okay, as a little bit of an addenda to the weak acid, strong base equilibria, let's go ahead and take a look at what that curve looks like again. So weak acid versus strong base again. Just as before with the strong acid, strong base, pH is listed over here on the left side. So we'll do 2, 4, 6, 8, 10, 12. Those are a little better spaced. And then volume of NaOH added is down here at the bottom. So we'll do 10, 20, 30, okay, based on just kind of our overall graph that we had. So if we went back and we plotted all the different points that we had done in the previous problem, in problem number 2, if we started off before the addition of any sodium hydroxide, we had a pH of 2.87. So that would kind of be the beginning point. Notice this is higher up than the pH for the strong acid, strong base one was to start with. After the addition of 10 milliliters of NaOH, we were at 4.57. So there's about 5, so about halfway down. So there we go. Notice in the last one we had a straight line basically until it almost hit the equivalence point. Here it's gone up some. Okay. At the equivalence point, which in the last case was 12.5, it went up just a little bit more. So that was the halfway. And then at the equivalence point, we were at 25 milliliters, and we went all the way up to 8.72. So there's about 9, come down a little bit. Again, just kind of ballparking it, but somewhere right about there. And then 1 milliliter beyond that, we went up to pH of 11.3. So again, just kind of ballparking that, seeing what the general curve looks like. So here, the line is not as straight across. It does go up, shoots up, and then it will essentially, I should have kind of stopped there, but then it will essentially level out again over here. So when you have the weak acid, it initially will go up a little bit. It acts as a buffer through this range until you use it up. Then you hit the equivalence point and it jumps up again, just like the other ones, and then it will level off to be straight again because it will dissociate any base that you have. So this was point A. This was point B, which was before the equivalence point. Point C was at halfway to the equivalence point. Point D was at the equivalence point. And then point E was past the equivalence point. So to look at what we had to do for each of these, for point A, we just did a basic pH calculation of a weak acid equilibria. Okay, at point B, we had to do stoichiometry first. So we did a BCA chart or the regular stoichiometry method to find out how much acid had been converted into conjugate base ion, and then we could use Henderson-Hasselbalch or a rice chart to figure out the pH. At point C, again, special point. At halfway, because the the acid concentration equals its conjugate base, the pH is equal to the pKa. At point D, we had to use BCA or general stoichiometry again, and then you have all of the acid is changed into the acetate ion, which then goes through hydrolysis. So you had to figure that one out. That's where you have to do, it's acting as the opposite. Find Kb if you had the acid, etc. And then at point E, you have to find the remaining moles of the base divided by the new concentration, or the new volume, excuse me, and then get the pOH and then the pH. So hopefully that might clear things up just a little bit.